ARC AGI is a set of challenges that are reasonably easy for humans to solve, but quite difficult for large language models to do so. And this is particularly true with the latest set of questions, ARC AGI 2, where there's a rather large prize outstanding for someone who can solve it, albeit not themselves as a human, but using the best possible approach they can come up with programmatically. In this video, I'm going to show you the three main strands of approaches I see for trying to tackle ARC AGI problems based on what's been done in previous years' competitions. I'm going to start off by showing you some very minimal examples just to give you a feel for how the approaches work, and then I'll go into quite a lot of depth actually solving the problems from ARC AGI 1. Now, before I start, Trelis Research will be submitting a team to ARC AGI 2, and applications are open if you would like to submit to be part of the Trelis team. I'll discuss a lot more about that right at the end of this video. Before I show you how to solve ARC with some kind of programmatic approach, let me show you how I solve it as a human. I'm here on arcprize.org, and I'll put this link in the description, but you can try out some of the challenges for yourself. Now, I don't think I've tried this one, so I'm going to have to figure it out for myself. The goal is, given some input examples that map onto outputs, so here's an input and it's converted to an output. Here's another input converted to an output. I have to figure out how this input here is going to convert into some kind of output. So I'll start off by just reflecting that I see different numbers of holes here on the top, and I suspect that that is going to reflect the color mapping. So here I have no holes, and this is mapping to the one with no holes, and the one with 3 holes is mapping to the one with 3 holes. Is that correct? Yeah, that is correct. And here, this is also the case, and this is also the case here. So let me see if I can, and it looks like I have two test challenges I have to try out. So is there a way I can copy from input? Yeah. So I've clicked copy from input, and now I'm going to use the fill. So if I have 5 holes, then I'm going to fill in yellow. If I have 4 holes, I'm going to fill in with this magenta color. And if I have 2 holes, I'm going to fill in with blue color, which looks good. And I don't have any plan for these other ones. So I suspect I will just leave them. Oh, I see. Actually, over here, this one is omitted because it's got 2 holes and it's not present. So it seems that I actually need to just blank these ones out. Okay, so I got that right. And the next one here, I'm actually not sure how. Oh, I guess I just copy from input as well. And if I find 1 hole, I'll just solve it like this. And if I find 2, then I'll do like this. If I find 2 here, sorry, that's actually 3, so that should be red. That's 3 as well, and there's none for 1. So I'll just black these ones, and I think I can submit. And it looks like I'm wrong. What did I do wrong? This one here is 4 actually, so that should be blue. All right, great. So you can see these tasks, I wouldn't say very easy, but given 5 minutes, if you're taking your time, you can work your way through them. And I'd recommend playing around with these. You can try out the first evaluation set. These are maybe a little bit easier from the first series of ARC, and the second series here is quite a bit more difficult. Now, let's move to the 3 broad classes of solving these. And the 3 I'm going to cover are first is, let me just describe them in lay terms. The first is coming up with a set of basic operations. For example, flipping the grid by 90 degrees or mirroring it across. And if you have a long list of these basic operations, you can just exhaustively try to combine them and see if eventually you get from the input to the output. This is called domain-specific language, domain-specific language approach. You're essentially writing a language because you're writing these basic operations that you'll then combine. And this approach was winning for a long time by IceCuber. It was winning up as far as, I think, just a year or 2 ago. So that's the first approach I'll go through. The second one then is using a large language model. And in the actual test, you're limited on the amount of compute, so you can't use a latest model like O3, for example. But we can use it for the purposes of demonstration today. And with a large language model, you could directly try to predict the output grid, but another approach is to predict a Python program that will convert the input grid to the output grid. And this is nice because if you have a Python program, you can test whether it is correct on the samples. So you could check whether it's right on these 3 trailing examples. And there's a good chance that if it's right, not guaranteed, we'll see that. If it's right on the training examples, you'll be able to apply it to the test input and know with reasonable confidence that your output is going to be correct. So those are the first 2 approaches. The first is combining these little operations. The second is writing a program, just using a language model. And by the way, you can write many programs and you can test them and only keep the ones that actually work, and then use the ones that work to submit your final answer. Now, the third approach then is to train a neural net. So you take these examples, you feed them into a neural net that's predicting the output, and you do lots of training and back propagation, like fine-tuning a language model, and it will be able to predict an output grid. And this is a general description for the winning approach last year. It was by training a neural net, but there are some modifications that improve the performance on that, which I will get into. One is that in addition to training it on lots of sample examples of ARC, including ones you make up synthetically, you get a lot of boost in performance if you additionally, at the time of making a submission, you grab these training samples and you further train the model during the competition, if you like, because that specializes the knowledge of the model and gives it a better chance. So you can take a model that's been a neural net that's been trained on lots of examples, then you further train it at the time of being in the competition on these training examples, and then you run the test example. And this is called test time training, and I'll go through how that works. And there's one further addition that can help you refine your choice of final grid. That's called depth first search. So if you've watched a lot about ARC, you might be familiar with that, but I'll cover it in a bit more detail later. So there we have the 3 approaches: domain-specific language, these little programs that we write, and then we try to combine them. Then we've got the LLM approach to writing Python programs, and then we've got the neural net training approach. So I'll now explain each of those in very simple terms with the help of ChatGPT, and then I'll go into much more detail by showing you a repo that I'm going to make public when this video is launched, called Trelis Research Minimal ARC. And within it, you will find links to very basic examples for each of those 3 approaches I described. And then you will find folders. So you'll find one detailed folder for domain-specific language, one for LLM GS, that's LLM Guided Search, which is inspired by the approach Ryan Greenblatt took. I don't use a lot of his improvements because I keep it very basic, but he took it a lot further. And then there's test time training, and I'll go into pretty big detail with running all 3 of these. So let's take a look at a simple level how the DSL approach works. And we can start by considering a much easier example than the ones I've shown you here on ARC. And the example we'll look at, so the little riddle or task that I'm going to create, is as follows. We're going to start with an input grid just of 1s and 0s. So you can consider just 2 colors. And we're going to have a training input that just has a column of 1s and a training output where there's a row of 1s. So you can probably see already that the operation here that's happening in the training example is a rotation. We're just rotating the grid so the rows become columns. And the question we're posing in this task is to consider this input and see if we can predict what the output should be. And given this is a rotation here, the correct answer to this input here is going to be a rotation. And the specific way I want to solve this is using a domain-specific language. So I want to set up a battery of basic operations, and then I want to run a search that combines these operations and see if we can find one that matches the training example. And if it matches this, then we'll apply it to the test example, and then we will have our answer, hopefully. So I've input this here. I've said consider this training grid of 1s and 0s and this test input. I want you to write a very simple domain-specific language type program with some very simple primitive operations and run a search to find a series of transformations that matches the training example. Then apply that program to the test. So here we have ChatGPT 03, just rephrasing the problem, the task that I've posed. And here's ChatGPT coming up with some primitive operations. So pretty basic stuff: identity, rotations, and then some flips. Now, obviously, this is a very easy problem because if we have a primitive of rotation and the problem I set is rotation, I'm setting us up for success. But you can imagine how this generalizes by having a combination in the training or in the test questions, a combination of these different operations. Okay, so we have the primitive operations. They've been identified here in some kind of a dictionary. And then we're going to apply the operations. And we're going to do a brute force search. And we're going to search for combinations of up to 3 of these primitives. So we're going to look at applying up to 3. We don't need 3 because it's just a simple operation, so it'll converge very fast after just trying 1. But in principle, and you'll see later on, we do need 3 or even 4. In fact, IceCuber uses 4. And it's kind of amazing, just 4 gets you pretty far, at least on ARC AGI 1. So this script is run, and I'll share this link so you can check it yourself. But basically, the solution that's found is rotation by 90 degrees. And if you do that, you're going to get this output here, which indeed is rotated by 90 degrees. And then if you apply it to the test problem, you take this test problem and rotate it, you do get the correct answer here. So yeah, this is pretty much it. This is the essence of domain-specific language. And to make it work, I'll talk much more about this later, you need to have a very good set of primitives. And by primitives, I mean simple programs, not just flipping, not just mirroring, but you need some more complicated ones like filling in the border of a color, of a color, maybe a patch of a certain color, filling in the right-hand side, slicing out the middle. So you can think up of all these basic primitive operations. And of course, the more you come up with, the higher the chance you might be able to get the right combination, but also the larger the search space. So if you have 40 different primitives, there's a lot of ways you can combine those. So it's going to take you longer to brute force search through all of the options. There are some things we can do to reduce the search space. So what we'll find is a lot of the operations, they will result in the same intermediate grids, and we can avoid ourselves recomputing intermediate grids by just keeping a table of those we've already considered. So there are tricks like that we can do to reduce the search space. But broadly speaking, this DSL approach is all about defining some basic programs and then combining them brute force one after another to see if we can get a match on the training pairs. And if we do, we then apply it to the test pair. Okay, let's move on to looking at this time the LLM guided approach. So here, the idea is the same. Well, the problem I'm going to pose it is the same. It's this basic rotation. So we expect it to rotate this and get the right solution. But I want ChatGPT to write a very simple Python program based on the training transformation that predicts the output of the test input. So, yeah, we're literally using O3 to come up with a Python program. In my later example, I'm going to use Gemini, which it's not as strong as using a model like O3, but for illustrative purposes, I've picked a cheap model I can run quickly. But here we're using O3 and it's easy, so O3 is going to get it. We've got a rephrasing of my problem, and O3 recognizes right away that one way you can match the training input to the output, one transformation, one way you can describe that. You can describe it with a rotation, but this is probably testament to me picking a bad example. You can also achieve it by doing a transpose, which is a flip, and you can get from input to output. And if you apply that flip, you will also actually, in this case, get the same result as if you do a rotation. So ChatGPT or O3 predicts the output for the training example correctly, and then predicts the output for the test correctly as well. And again, a very simple example, but if you expand this to more difficult problems, you're again going to try and ask your language model to create some kind of Python program. You will then run the program, and if the program does match on the training example, you can consider there's a good chance it's going to be the correct program. Particularly if there are multiple training examples and it's correct on all of those, that means the program is pretty likely to give the correct test output when given the test input. Now, why wouldn't it give the correct test output? There may be different ways to achieve the training transformations, and we'll see that actually in one or two of the ARC AGI 1 problems. And this is probably part of the reason why in ARC AGI you can submit not just one answer, but two answers. So even if there were kind of two ways to get the training transformations, you can submit two answers for the test which allows you a bit more flexibility and definitely makes overall the challenges a bit easier. Now, why doesn't this work very generally? Well, when you have small grids, the language model doesn't have much problem recognizing the structure. But as the grids get bigger, it's very difficult for a language model to see patterns, particularly messy patterns like the one that I solved earlier. So here, well, I'm on the first task, but if you go back to one of the ones that I solved, like this one here, this is going to be very messy. And if you ask a language model to describe this in abstract terms and say something like, there are 2 green blobs on the left that have one hole of size 2, and to the right of that, there are 2 yellow blobs. And then just below that, there's a red blob with 3 holes of size 1 each. It will have a very difficult time giving that kind of description that I just gave. And if you can't describe abstractly what's happening here, that makes it very difficult to understand what the transformation is. That's why it's called ARC, Abstract Reasoning Challenge. And yeah, that's what makes this very difficult. So this is the second approach. The third approach now is neural net. So with neural net, the idea is you take lots of examples and you train a neural net given these examples and given a test input to predict the correct output. So let's take a look at this one. And my prompt here, let's consider the following task. My task is the same. It's just that rotation or transpose, it turns out. I want you to write a very simple program in NumPy to train a tiny neural net that is autoregressive and uses attention. Now, you don't have to do this. It doesn't have to be autoregressive. But since transformers are working in many domains, the winning approaches, at least in 2024, have also been transformers. And they typically use small llama models, sometimes a T4, T5 model from Google. I'm not sure that much of the language ability is really being leveraged. It's really just that they are transformer models that contain attention, which means they are able to characterize the relationship between all of the input tokens. So I'm going to ask GPT here, what you should do is define a training data set with some basic transformations. They should have train and test examples. So I'm basically trying to get it to make up some training data here. Now, it's definitely a bit cheating that it knows in advance what the test problem is going to be, but nonetheless, I wanted to create some training data. And when making the training data set, do not use the task I showed above, because that would be cheating. Do create a variety of simple task examples involving various operations to generate them. So I'm actually kind of getting it inspired to use a DSL type approach, domain specific language approach, where it's using basic programs to create test examples. If you want a repo or an approach that does that, you can look up ReArc or ReARC to generate lots of synthetic data. B, train the small neural net. Just train on CPU, because I know that ChatGPT will not provide me access to a GPU here, although maybe sometime it will. That would be cool. By the way, data for the training should have a train example followed by a test example, and focus the loss on the test output. This is a nuance we'll get to later, but we have to flatten the whole problem. So we're going to flatten the whole examples. We're going to have the problem part and we're going to have the solution part. And when we back propagate through the weights, we typically want to weigh the update on how far the solution is. We don't want it to be trying to predict what the next part of the problem is. Now, you can kind of see intuitively why that might make sense, because you want the model to really focus on getting the answer right, less the problem. Actually, it's empirically found to be the case too. It turns out that you want it to be good at finding the solution to the test problem, but also the solution to the training problems. Because remember that the full task description is a series of training problems, which will go training input, training output, training input, training output, then test input, test output. And it turns out you do well by turning the loss on for all of the outputs, the training outputs and the test outputs. If that's not clear, don't worry, because I'll go over in more detail later on. And then C, run the neural net on the example above and see what you get out. It thought for 10 minutes and 10 seconds. So, I mean, this is pretty good. The result is pretty good. So we have a tiny autoregressive net with attention in NumPy. I didn't use PyTorch because I was worried it might try and use CUDA or something. We're going to have a sequence length of 27 because we've got 9 training inputs, 9 training outputs, and then we've got 9 inputs. Now, you know, in ARC, there are typically multiple training examples. So this is a simplified version, only one training example, and then one test input. It's going to make a pretty small model with just 8 embeddings and a vocab size of 2. So we're doing binary arc, 0 and 1, instead of having the full possible 10 colors. Now it's created a few helpers here to make up some test questions like rotating, flattening, make meta sequence. And it's then going to set up the embeddings and attention weights. So we are going to have attention within this, which is defined here. Here's your queue, your query, your key, and your values matrix. So we're defining attention here. We're making the features. We're making some examples here, and we're defining a training loop. So it's a really simple loop that's going to train this very small neural net. And when we're finished training, and it defaults to a very large number of epochs. Actually, it's a very high learning rate too, but it's a tiny neural network, a large number of epochs. And then it's going to run, once it's trained the net, it's going to run the actual example, and we're going to see what we get. And ta-da, we actually do, we train in 5 seconds, so very small neural net, and we do actually predict the correct test output. So yeah, this is pretty much how the neural net works, and it works very well if the problems are easy. Once the problems get harder, it does not work so well, but we will see some tricks that help improve. And one of those tricks is, well, let me start with one of the problems. One of the problems with this approach here, when you try and predict the output using a neural net, you don't know if the output you're predicting is correct or not, because obviously you don't have the answer when you're doing the competition. And since you're not predicting a program, you can't check if the program is correct on the training examples. And moreover, you're using those training examples to train, because we're doing test time training where we train the model initially and then we train on the examples. Now here I didn't actually train on the specific example, at least directly. So I'm not taking the full test time training approach, but we don't have a way to know when we do make a prediction if it's going to be correct. And because if you're familiar with language models or any neural networks, there's this concept of temperature, which introduces randomness in how we select the next token. We actually can generate multiple outputs by varying the temperature. And we don't really know which one of those we should submit as a final answer. Now, typically we will set the temperature maybe to a low value so that we will pick the most likely next token. I should be careful not to say the most likely sequence of tokens because there's a nuance there. But typically that's called greedy decoding. We'll take the most likely prediction. So it will predict 0, then 0, then 0. And maybe it's like 51%, 51, 51, 56, 59, 60, 70%, 90%, 90%, something like that. That's how greedy decoding would work. But we could also sample at each point and we would have different sequences. And actually you can leverage this to our advantage. So we can decide to do a few different statistical approaches. The easiest to understand is called beam search. So what beam search does is it's going to consider a certain number of parallel streams. So we're going to decode the most likely token, but also the second most likely token, which in this case, there are only 2 tokens at the first step. And then we will proceed step by step, and we will hold on to the 2 most likely sequences as calculated by the tokens we've seen so far. So we can actually continue on this prompt here and say, okay, this is good. Let's extend and run the script to do 2 things. Let's do beam search with a width of 3. Now it's going to be a max width of 3 because at the first step, it can only be 2 wide anyway, and print the outputs and the probabilities of each. And then we're going to do another approach, which is called depth first search, which works out well. We'll see that later on, with a threshold of 5%. And how depth search first works is instead of keeping a beam of the possible tokens along the way, we actually calculate one sequence all the way to the end. So we make a full prediction. We predict a full grid, like this grid here. And then we backtrack. So we will kind of say, okay, I have this full sequence. This sequence is a probability of 15%. And usually we'll have a threshold percent we want to be above to keep considering it. And I'm going to say, okay, can I find another sequence that's above a threshold by backtracking by 1 step? So we'll throw away that 0. And let's look at the next most likely token, which in this case can only be a 1. So we look at the 1 and we'll see what's the probability of this if it ends with a 1. and maybe the probability is 0.1%, so it's too low, so we'll throw it away. Then we backtrack again and we say, okay, what if this 0 here was the next most likely color? So here we'd say it's a 1, and then we've got this as a 1, and we go forward again, and we take the next most likely token. If this here is a 1, then we look at the most likely one after that, and we calculate the full sequence probability, and again check if it's above a threshold like 5. So this is called depth first. Basically, you run out a full sequence to the end, and you start backtracking, and you only keep sequences that are above some probability threshold. And where this works well is it provides a very exhaustive search if you set a threshold, and if you also have kind of spikiness in the probabilities. So basically, when the language model I shouldn't call it a language model, when the neural net makes a prediction of this grid, there are really only a few grids that are going to be high probability if your model is good. If your model is bad, all of the grids will be similar probability and you will have no idea which grid is good. But if the model is good, there will be a few in particular that have kind of spikes in probability. And doing this depth search is going to be useful because it's going to kind of find the main parts of those grids, and that's going to have high probability. And then it's going to search around with little variations around that kind of high probability, and it might just find the right grids that are on those spikes. So if that intuition didn't fly, don't worry, because you'll get a second shot. But we can run this here, and it does pretty much the exact same thing. This is all more or less the same code. Difference now is that it's going to decode in a few different ways. So here it's doing beam search with a width of 3, depth first search then with a 5% threshold. So we're only going to keep sequences or grids, you can say output grids, that are above 5% chance. And in beam search, it finds 3. And I think it's normalized the probabilities to the top 3, which I don't like actually, because I wanted to know the absolute. But anyway, it's got this as the most likely grid, the correct one. Second most likely is this. Third most likely is this. And with depth first search, it only finds 2 grids that are above the 5% threshold. And it's maybe normalized based on the top 3. I'm not quite sure. Maybe this is absolute. I doubt it. Maybe it is. Either way, you can see that in this very simple example, the beam search and the depth search are finding the same most probable example. But where the depth first search comes really into play is when you have a longer grid where you're going to have a much larger solution space. And if your model is somewhat good and you have spikiness in which grids are correct, depth first search might be an easier way to do an exhaustive search. You can be exhaustive with beam search, but the problem is you don't know what beam size to use a priori. And you also may have your beam way too fat at the start, and you might be trying to solve a lot of the colors, like you might be looking at all 10 colors from the very start, when in fact, realistically, the first color has to be a 0, and therefore you were too wide with your beam at the start, but you should have been wide at the end. And depth first search, if the distribution is spiky, can end up being a good approach for doing this. So with that, I've covered the 3 main approaches, and I'm going to move into the minimal arc repo here. All right, so I'm going to clone this into Windsurf and take a look at the README. So a few things in this repo. First of all, there's some data, the ARC data. There's a clean version. I'll briefly talk about that. And then there are the 3 approaches. So there's DSL, domain specific language, LLM GS, LLM Guided Search, inspired in part by Ryan Greenblatt's approach, and TTT, test time tuning or test time training. Just a few notes on the data, then I'll go through these one by one. We have here the ARC AGI 1 tasks, and there are training examples, so training challenges, and then the solutions. And there are also evaluation challenges and solutions. And then lastly, there are test challenges, which are the problems that you had to solve to submit an entry into the competition. And for that reason, there are no test solutions because those are hidden, so people aren't able to overfit on them. But the broad principle here is you should train on the training ones, training and solution. So whatever approach you're taking, you want to train on those. And then to test yourself, you use the evaluation challenges. That's the idea. Now, I'm sure plenty of people, and there's nothing particularly wrong or illegal about this, it's probably smart, are using the evaluation challenges to do training as well. and augmenting those, because ultimately when you submit, you're being tested on the test challenges, which you can of course do some test time training on, but you won't see the solutions. So you could just train on the training split of those. You'll see more if you don't get what I'm saying later on. Now, one last thing I need to mention on data, two last things. One is these challenges here, they have a number of training examples. So if we look, sorry, this is really hard to read in this format, but here, for example, here is the training examples from this problem, 005. So we have a number of training examples with inputs and outputs. We've got two training examples, an input and output for each. And then we have one test example with just the input, obviously, because the output is provided in the solutions. But some of these tasks, and I'll use the word task to refer to this entire thing here. So this is a task, it has a task number. This here is a task. It also has a task number. It's actually a much bigger task because I don't see the next one for quite a while. But either way, some of these tasks, most of them in fact, have got one test. So they'll have one test input and one output, but some of them have got two test inputs and you need to separately solve those. And for the purpose of doing training, especially when we do the fine tuning, it's just easier to only have one test example and then to do training on that. So for that reason, we clean the data set to split any examples, any tasks rather. I should be careful with that because by example, I mean input output pair. Any task that has two test examples, I split it into two separate tasks. So that means every single task in the data set will have exactly one test input, and it increases the data set by a tiny bit. So if you want to run that, you can just run clean ARC data. By the way, this isn't something I came up with. It's in the sample notebook for ARC AGI 1 in Kaggle. But you can clean the data and it says keep only examples with single tests, but it actually splits the examples. It splits the tasks so that you have two tasks if there were two test examples in one of them. Now, something else that's useful is to segment your data. So there are about 400 evaluation tasks, I think 419 after you do that, splitting. And there's a paper on test time training by a group from MIT, and it splits the problems in the eval set. It takes a subset of 80 out of the, I think 200 or 400. And then it further categorizes them as easy, 20 easy questions, 20 expert, 20 hard, 20 medium. And then here's the full MIT split here. And the reason this makes sense is because you don't want to waste a ton of time evaluating. It makes way more sense to focus on easy questions. When you get them all right, then you can move on to medium, hard, etc. So for today, because we're looking at minimal approaches, we're just going to look mostly at trying to evaluate on these easy, MIT easy questions. And I'm calling them that because they're identified as easy by the MIT paper. So that's the ARC data. The clean data is here. So it's exactly the same, but you won't find any examples with two tests because I have split them up according to the cleaning script here. If you want to run the cleaning yourself, just cd into the ARC data folder and run Python, uv run Python clean ARC data.py. I guess if you want, you should set up a virtual environment, but I don't think there are any dependencies, so you should be able to just run that. So with that, we're ready now to move to the main three folders. I'm going to reorder them a little bit here because we'll start with the domain-specific language, then the LLM Guided Search, and then the test time training. So let's move into the domain-specific language folder and take a look here at the README. Okay, so you'll remember domain-specific language means we come up with some basic kind of operations, and then we need to chain them together and just try and exhaustively search. And IceCuber did this using a search depth of 4. So that means trying to find combos of 1. That's not a combo, but just one of these operations, then combos of 2, combos of 3, combos of 4. That's as far as IceCuber went, and I think was able to get close to something like, I might be getting my numbers wrong, but mid double digits on ARC AGI 1 in terms of percentage correct on the hidden test set. And by the way, the hidden test set is known to be harder than the public evaluation set. So if you look at the data here, it's basically known that this on ARC AGI 1, the test challenges are harder than the eval challenges. And I think maybe that's the case on on ARC AGI 2, I think maybe to a less degree because it's more carefully human benchmarked. So we need to gather some basic primitives. And I'll just show you some of the primitives here. We can look at DSL utils and then primitives. And there's a big long list of primitives that we have here. Some of them not too dissimilar from the simple ones earlier. Here's a rotation function, rotate 180, 240, flip horizontal, flip vertical, transpose, flip diagonal. This one catches a few in ARC AGI 1, apparently it's important. Flip anti-diagonal, shift. So shift the cells up, shift them down, shift them left, shift them right. Fill in holes by flooding, fill in a background. So you can see we have a wide variety of different functions here. In fact, I think I have about 27 different functions. And the way that this works overall is we're going to set up a program, and the program means a series of these simple operations. That's what program means. So I'm not going to go through the program script, but essentially it will cobble together multiple of these operations. And if that program solves all of the training examples, of which there might be usually 1, 2, 3, or 4, then we consider that a valid program, and we will use that to calculate a test output. Now, I've made this, even though it's a minimal example, I've made it so that we can run search in parallel, so we can use multiple cores. I'm on a Mac. I think I maybe can run 12, but I'm going to run typically 10 kind of searches in parallel. And it is just brute force. You start off, you look at all the single programs, then you start looking at pairs, then 3, and then 4. Now the key, I'm going to talk through a few of the keys here to making this work, and I'm in the wrong README. Should be in the README for DSL. The first key is that each of these programs that I just showed you, they need to be unary. And what that means is when the program is called, we shouldn't have to specify any input parameters. Everything should be automatically set up, just given the size of the input grid. So if we say flip, we pass in the grid, it's flipped. If we say fill border, we pass it in, it flips the border. But there's no other parameter that somebody has to manually control. Like if it's a shift upwards, we don't have an input saying shift up 1 or 2. In fact, if we want to have that, we should consider them as separate operations. So we would literally have an operation for shift up 1, another for shift up 2, another for shift up 3. And you can see that actually when it comes here to, I think, coloring. There are different variations of the coloring. Well, I won't give the coloring example because there's a shortcut that I've implemented on that. But here you can see for masking, we literally have masking, I think, column 1, column 2, and column 3. So we're not even, there's no ability to mask columns 4, 5, 6, for example. We just have this limited set of operations, which of course could be improved on. But my point is that when we pass in, when we decide on a given operator, we need that operator to be unary. So it just takes in an input of the grid and it does that operation, because that allows us then to chain together a program. But it means that our operations need to be pretty specific on the other hand. So that's the very first approach. Now, when it comes to picking primitive operations, you want them to be broad and you don't want there to be too many, because so you have this trade-off because you want your operations to be fairly specific because you're not able to tune any of the knobs on a given operation, at least with this raw DSL approach. But you also don't want too many primitive operations, because if you have, say, 1,000, there's just far too many possible combinations to search through in order to exhaust the search space. So you kind of need to be careful in picking the right operations that are going to be right from an elementary standpoint. And how do you know which ones are right? Well, I guess you would just run this whole approach on a set of training data and you see how that performs. And hopefully that will be correlated with it doing well on the eval set. Okay, so I'm going to just run this code, even without having explained everything, just so you see what's happening. And then I'll come back and I'll comment on two of the major improvements I made in order to speed things up. So if you're cloning this, you can just CD, and you need to be in the DSL folder. Okay, so I'm going to start by making sure I'm in the right subfolder DSL. And if you're cloning, you can just do UV sync, check all the requirements are in sync. And then I'm going to run one of the tasks. Now, I have cherry picked this because I know it's one that is solved by this approach, but that's going to be instructive. So we're going to run this task ID to a depth of 4, like IceCuber, Show just means we'll show visualization. We're going to use the data in ARC Data Cleaned. We'll apply a 60-second timeout. So that means we'll only allow a maximum of 60 seconds for searching. It will actually exhaustively search and find a solution in this case. And we'll pass in debug just to show some full debug information. Okay, so that was quick. Let me expand a bit my screen. And what we can see is we've used 27 primitives. So 12 basic operations, 3 color mask, 2 tiling, 2 crop, 2 replacements, and 2 flood fill. We've run this task. We've only run with one process, so we're not parallelizing here. And we found that the prediction matches the solution. And you can see that the correct program involves 3 steps. So tiling 2 by 2, then rotating by 180, and then cropping the center half and keeping it. Now, actually, there are a few programs that will work. If you flip the order of operations here, it still works. So you'll sometimes find different programs, but they end up being equivalent and they will give the correct solution. Now, I can also show you the visualization here. So this is the task that we have just attempted. Here's the train input, the output, the input, the output, the test input, and the test prediction, which is correct in this case. Now, notice how for us, this is a very easy problem. Essentially, we're just floating these inner squares to the outside. And here we're floating them to the outside and here as well. And yeah, I mean, that's not a precise, but you can tell by my description what I mean when I say kind of float or expand the inner patches to the outside. But the solution that the discrete search gets is very different. Let's take a quick look at the solution. So the solution here is to tile, so to take 2 by 2 tiles. So basically it's going to take this here and it's going to make a copy to the right, and then it's going to make a copy down here, and then it's going to make a copy down here. So you can imagine converting a 4 by 4 into an 8 by 8 grid. And then it's going to rotate the grid by 180. So it's going to turn it all the way around. And then it's going to crop the center half. And it's actually hard to visualize this. I can just barely visualize it. But effectively, it's going to grab these 2 squares, then the 2 here, the 2 here, and then 2 more rows of 4 below that. And because it's rotated 180, and because we're just grabbing those and it's been tiled, it actually does end up with this pattern. So basically DSL has found a solution here, but it's a pretty indirect way of doing it that does work. And I guess that's part of the charm of the approach, is that sometimes just by brute forcing a few combos, you might get to a solution that you could also just get to in one simpler step. But there's no straightforward primitive that we have that just says float the middle ones out to the outside. So we weren't able to do it in one step. So this is a demo of solving just one problem. What I want to show you now is how to solve multiple problems. And we're going to solve all of the ARC MIT easy ones. So we'll run this here and we'll set a timeout of 60 seconds. Now this is running with parallel processes. I think I have 12 cores, so it's using 11 of the cores on my laptop here. And it's going to progress through the 20 different problems. And then we'll be able to see there are a few reasons each program can stop. One is the program is correct, or it has a valid program. We don't know if the test is correct, but we know if it's valid according to training. Another is that it exhausts the search space. So it's literally searched through all combos of 4, 1, 2, 3, and 4 programs. And the last one is it just hits a 60-second timeout. And so we'll see that happening. There'll be an example of each of those when we get to the results. And here we have the results. So we've got our 20 tasks. The first program, and this is the one I cherry picked, was correct. And that's the rotation, the tiling, rotation, and cropping solution. It took just over a second, so extremely fast. And it visited 524 states. So these are intermediate grids. And now comes to one key shortcut that IceCuber introduced, which is that you cache. So you keep a list of all of the intermediate states reached for a given problem, because you will often reach the same states. And then when you reach those states, you just prune. You won't continue from that state because you already know from there where you're going. So by caching a list of the states that are intermediate, you can greatly reduce the amount of attempted programs that you run because you're just going to avoid a ton of duplication. Okay, so then the next one here, we exhausted the search. So what this means is basically for solving this task, we didn't have enough primitive programs, or we didn't have the right ones, because we did look at all the combinations, but none of those combinations solved this. This one here failed. So must have hit some bug in the program. I'd have to diagnose more exactly. Some more search exhausted. Here we found a valid program. I don't know how many steps it is, but it's got a few steps here. We found another valid program. And then the last two here, we just timed out on. So they hit the 60 seconds and then the program stopped. And it looks like so far we're able to get 3 out of 20 of these approaches correct. Now there's one other trick I'll mention that I did include. I didn't include all of the ice cuber tricks, but there's also an approach to stopping early. So if you are, say, expanding the grid, so you can have an expansion through, let's say, tiling or something, sometimes you might take a series of operations where you expand the grid or you expand the number of colors to such point that in the remaining steps, if you're already at the 3rd step out of 4, within that last step, there is no operation that is going to possibly bring you to the output training grid. And we can run a series of checks if that's true. And by doing that, we can stop searching early in a lot of cases, because often we will take a certain path of adding colors or expanding such that there's no possible operation that could bring us back to the final grid. And yeah, just by tracking basically the size of the grids, the number of colors, some basic metrics like that, we're able to do these quick checks at each stage that basically allow us to stop the searching at those points. So this kind of early stopping reduces the problem space a lot. I think it reduces it maybe by a factor of 5. By the way, adding the hashes for intermediate states and not repeating those, that reduces your search space by, I think, well over a factor of 10 as well. So these are 2 very big speed ups that you're able to introduce on top of just naively searching the full program space. Now, something I'm not doing a lot of is what's called heuristics. So everything is more or less brute force. I'm just searching for these operations. I'm not saying, oh, I have a grid that has 2 greens on the left and 2 on the red, and therefore I should consider a rotation as one of my first operations. That's a kind of heuristic, and I'm not doing a lot of that. One of the only heuristics I'm looking at, because this is a minimal approach, and we can see it here if we look within search and heuristics, I do have one simple heuristic around the shape of the grid. I do have one on symmetry as well, but the shape heuristic just says if the inputs are the same as the outputs, there's no point in doing expansion operations or contraction or tiling maybe, because you have to end up with the same size grid as the output as the input. So you can reduce the number of operations that are going to be allowed. You can see we've got a reduced set of allowed operations if we have the output shape equal to the input shape. So this is not a very efficient way to do things using a domain-specific language without having a lot more heuristics. And you could think about even training a neural net to help you decide which of the programs you should start with or continue with. And that leads you into a class of approach, which is also called dream coder, where you train these neural nets to help guide you in picking certain operations so that you can more accurately pick the operations rather than brute force across the full search space. So this pretty much wraps up the DSL. I'll let you play around a little bit more if you want by yourself by going to the search, by going to the repo.
Next, I'm going to move on to LLM Guided Search. So I'll head into the LMGS folder and take a look at the README there. Now, this is an implementation of using Gemini Flash 2.0, although I might switch it to 2.5 since that model has just come out. And Gemini is being used to generate Python programs. It's been given the input and output training grids and also the test input grid. And then it generates a program that would convert all of the inputs into the output grid. And those programs are tested on the training examples. And if they pass the training examples, they're considered a candidate program for generating an output from the test input. Now, it's possible to find multiple programs that are going to pass this. And if I find multiple programs, I use majority vote. So I look at the program outputs, the test outputs generated by those candidate programs, and I take the program that, or rather, I take the output that is generated by the most programs. If there's a tie, then you just have to take one of them. In the ARC challenge, when you submit, you can submit 2. But in this case, I'm just scoring based on 1. So that will penalize my score a little bit compared to if I'm allowed what's called pass at 2. So just keep that in mind. All right, I'm going to again just try and run this without explaining too much, and then I can get into a bit more detail. As I said, broadly speaking, there's program generation. Once all the programs are generated, I test them, I filter them out based on whether they pass on the training examples. And then lastly, I do majority voting based on the test. I run all of them on the test input and get the output. Now, for doing the filtering, that means I have to run the programs. Generally speaking, the LLMs are going to create programs that are fine. They're probably not too dangerous. Maybe they could have infinite loops, so you want to have at least a timeout on running the programs. If you want to be extra secure, you can run the programs in a sandbox. I've talked before on this channel about using the Pyodide sandbox designed by Pedantic AI. So there's an option by default whereby the programs will run in that sandbox. Actually, it takes a bit of time. It can take about a second to spin up the sandbox, even though it's pretty lightweight. So I've alternatively, if you pass in the argument no sandbox, then it will not run in a sandbox, but it will run in kind of a local Python-based sandbox I've created that has got limited imports and has also capped the number of total operations to, I think, 1 million. So that's like providing some level of security, not full sandboxing, but hopefully the risk is relatively limited here. The LLMs that I'm using are probably not likely to have vulnerabilities. But as I said, putting in a timeout is important. Otherwise, you could just have a long runtime. And these programs are very simple. If it's a cracked program, it should run in just a few tens of milliseconds at most. So really, there should be no reason the program should be taking much more time than that. Okay, so if you're cloning this, you can just use UV sync. I'm going to CD into this folder, which is LLMGS. I'll sync my dependencies. You do need an API key. I've set this up for open router, which allows you to access any model. I think it charges a 5% premium over what the actual endpoints would charge, but it allows you to cap your usage by having an API key with a fixed spend amount. So I've set that API key in my environment variables, and now I'm pretty much ready to run. You need to run here with MCP. That's because the Pyodide sandbox is an MCP server. You can pass in a task ID. Now here is K, the argument K. This is the number of programs to attempt for every problem, for every task. And the larger you make this, the more likely you are to find some valid programs. And this is where you see kind of scaling. If you increase K, typically if you double K, you're going to get, if you exponentially increase K, you're going to get a linear improvement in performance, typically. And last of all, so by the way, if you pass in K, you then pass in an integer for the number of programs. And then there is the visualize parameter here, which will let you visualize just as I did previously for DSL. Okay, so I'm going to try run a specific example. If you're going to run with an MCP server, you need to install Dino, and then you need to run the server so that it's available to spin up sandboxes. But I'm going to run with no sandbox, so I'll just run a lightweight local executor. And I'm going to start off and run this task here. And I'm going to do it by running 8 programs. So let's paste that in here. And if you want to check what model is being run, you can go to core and then generate programs. And you'll see here the specification of the model that's been chosen. If we like, we can maybe swap that. So if I go to open router, and if I look for the latest Gemini model, the Flash, could use Pro would be better, but I'm going to be cheap. So let's copy this here, Flash preview. Now will it throttle me? I think this is a paid endpoint, so probably I won't be throttled. And I can adjust this. Yeah, I mean, that's just some guidance. So put this in here. And by the way, I'll just cancel this and I'll rerun it. So it's going to generate 8 programs. It'll take a bit of time because they're possibly going to be fairly long. I am using a prompt whereby it is allowed to think before providing the program. But we can check here the prompt. If you go into prompt template, here it is. You're an expert Python programmer. Learn the grid-to-grid transformation from the training examples and write a complete solution with a solve function. So this is key because we're going to extract the solve function when we want to run that program. First, provide your step-by-step reasoning within think tags. This is not a thinking model, but we can still get it to think. Would a thinking model perform better? Yes, it would. These models like O3 or probably Gemini Flash thinking would perform better. And you wouldn't necessarily need it to think in that case because it would be trained to do so. Then I give an example. Think, looking at the examples, okay, this is just an example of writing one program. And then I provide the complete solution, including the solve function. And I give it some guidance on what types of imports it can use and how it should write it. The function must be named solve. Then I pass in the training block. This is the training examples, inputs and outputs, and the test block, which is just the training input. And then I reiterate, first provide your thinking in think tags, and then your complete solution code. So this is the code that we run in. It gives us back a program. That program can be extracted using regular expressions, and then it can be passed to the sandbox, either the lightweight container or the full sandbox, and run. And when it's run, we can run it on the training inputs. We see if the outputs are correct based on the training outputs, and then we run it on the test input. Now, actually, to save time, I run it on all of the inputs, including the test input as well, so that if the training inputs are correct, then I already have a copy of the output grid. Now, many of these will fail, and the programs just won't be properly set up to give any output, in which case you just discard them. So I've run this here. It's returned 8 different programs. Only one of them was valid, which means only one of them was correct on the training examples. And it took about a minute. And here we go with the visualization. So you can see the training input, output, and here's the prediction, which is matching the output here. I noticed this grid superimposed. Probably should get rid of that. Second training example is correct, and then the test input, ground truth, and then the candidate output. So for many of the simple examples, just taking this approach works pretty well. So let's extend it and see how we do if we run on the full MIT Easy set. So I'll go back to my README, and let's scroll down, and we'll find a little script that allows us to run on a full task file. So here we can do UV run main with a task file of MIT Easy. We can specify the input data file because the MIT Easy is a subset of the evaluation challenges. We'll run with 8, so things don't take too long. 8 attempts. Concurrency of 32, so I've written the script so that I query Open Router in parallel just to speed things up. And then we'll save the results to this results folder here. We will visualize and save the visualizations so we can look at all of the outputs, and we'll use the lightweight sandbox. So I've got the no sandbox argument being passed there. And while this is being completed, just a few notes on this approach. As I mentioned already, I'm just taking one answer for submission when I consider scoring, which is more strict than the standard pass at 2 metric that ARC uses. So ARC allows 2 submissions. So I will perform worse for that reason. Second of all, I'm only sampling 8 different programs. Whereas if you look at, say, Ryan Greenblatt's approach, he's sampling many, many, many more, I think up to thousands of programs in some cases. So performance there will be a log of that number better. So it will still be significantly better. And furthermore, there are a lot of optimizations that have not been introduced. You can check out Ryan Greenblatt's blog. Notably, he uses few shot prompts. So we kind of provide an example of the output format with a Python program and some thinking, but we're not providing few shot in the sense of providing training examples, test input, and then an output program. So we're not strictly offering few shot examples of the task at hand. Furthermore, if you split the tasks into 2 categories, basically there are 2 broad categories of ARC tasks. The first is categories where output grids are the same size as inputs, and the second is where output grids are not the same size. And just by making that split, you can have a specific set of few shot examples and also instructions and just making the split will improve the performance as well. Furthermore, we're not trying to revise any Python programs if they're badly written, but you can easily know if a Python program is not executing, and so you could send it back to the LLM to get improved, or you could send back a subset where the Python program generates an output that's maybe close to the actual training outputs, but it's not quite there. Last of all, feature engineering. So we're just feeding in the grids as pretty simple arrays with commas, but you could try and put in other representations, like maybe ASCII representations. You can also put in diffs, so a difference between the input and output grid. That's particularly useful if you have input and output grids that are the same size, because you can just do a diff between the two. Also, when you're trying to revise a Python program, you can also provide a diff of what it thought the output should be versus what the training example output actually was. And those diffs and the alternative representations can improve the performance quite a lot. And actually, for the sake of time here, but I'll go back and use the previous model. So I'll use Gemini 2.0 Flash, which I think is providing faster generation times. And I'll run that file. And yeah, I've started this script again. I'm just running with the Gemini 2.0 model, which I think is giving me a higher rate limit. By the way, using concurrency of 32, it's not fully helping me because my program size for each task, and I'm operating on a task by task basis, is just 8. So I'm only using a concurrency of 8 here at most. In principle, if you wanted to optimize this even further, you would concurrently generate programs across all of the tasks so that you could use up that full level of concurrency. Now, something else to note here is the prompts are very long. This is well known in ARC that as you get longer or larger grid sizes, they can go up to 30 by 30. Those problems become a lot more challenging because it's very difficult for the language model to reason across such a long context length and to visualize patterns, particularly abstract patterns that are within. Now, you can shorten the prompt quite a bit by using a more terse type of syntax. Currently, when I input the numbers, there's a comma and a space between each number in the grid, but you could actually just get rid of that and you could put in spaces, or you could even, if you greatly simplify your tokenizer, I'll talk about this when we get to the neural net approach, you could literally have a tokenizer that only allows for numbers and perhaps a new line token as well. So that allows you to reduce the size of your prompt significantly, which can then make it easier for the model. Although the model needs to be then maybe retrained if you're using such a terse type of approach with a different tokenizer. But anyway, this allows you to significantly reduce your prompt size. Another thing you can look at is the generation tokens. So this is moving fairly fast, but you'll see that naturally the shorter completions are coming back first, and then it's the longer ones we have to wait on. And if you have a very long response, that's maybe indicative that it's just going a bit off the rails. And potentially what you should do is cap the max tokens that you're allowing to be generated. Now you'll see there are some failure notes here. This is because we are trying to run some programs that are failing because the program is not properly handling the grids. So it's just an example of a failed program. But interestingly, you can see that the Gemini 2.0 model compared to 2.5 Flash, it seems to be a little bit better behaved. I'm looking at the completion tokens, and the number of completion tokens seems to be fairly short in a lot of cases. Now, I am seeing failed programs, but I was seeing very long completion token numbers up in the thousands for the Gemini Flash 2.5 model, although it's a preview model, so who knows exactly to what degree that might change before the actual release. Okay, everything has been run now. You can see how fast that was compared to running Gemini Preview. 20 tasks, 2 had valid programs, and there was 1 task that had a correct text prediction. Now, this is kind of interesting because it means that we had programs that passed on the training examples, but failed on the test examples. And our majority vote was not able to pick out the one that was deemed correct. Now, keep in mind, we're just doing pass at 1, so with pass at 2, it's possible maybe that would have passed, but we'll take a look at some of the visualizations, and that'll help us understand. So we can go to LLM generation guided search and then visualizations and MIT easy. And we should be able to have a look here at some of the grids. So here is the very first task. And you can see we do have a generated output, but it's not correct. So the candidate is marked with an X. In the next case here, we also have a generated output. Now, the generated output I'm showing is the winner of the majority vote. And if there's a tie, I'm showing the first example. And if there are no programs that pass all of the training cases, then I'm just showing the first output that was generated. I'm showing the output of the first program that was generated. So yeah, in both of these cases here, we're not finding a program that passes the training examples, and I'm just showing the wrong test output, or the test output from one of the wrong programs. So these two wrong. This one here, wrong as well. This one here is wrong. And we'll keep going until we find one correct. So for this task, ignore the grid superimposed here, but we've got a program that is correctly predicting the output here, correctly predicting the training output, and then it's also correctly predicting the test output. So we'll keep going. This one here, wrong. Here, yeah, we have a program, but it's a wrong program. Same. Now here, this is an interesting case because we have a program. It's predicting the correct training outputs in these three examples, but it's actually predicting the wrong test output. And you do see this sometimes. And this is maybe part of the reason why 2 submissions are allowed in the ARC challenge, but you can find programs that will pass the training examples and they will fail the test examples. And I know this problem here tends to lead to that kind of outcome. So yeah, this is why we have a program that is being marked down here as being valid, but actually it's not passing the test. It basically means there are, in principle, multiple interpretations of the training problems that lead to training outputs, but are not compatible then with the test, which is, I suppose, not really great from a rigorous test standpoint, from a test design standpoint. Okay, so I've already showed you the one that was correct and the one that was a valid program. So all the rest of these are going to be incorrect. We're just going to see output programs, but they are not going to be matching either on training or on test examples. And so that is the overview of the LLM guided search method. As I said, you can improve performance quite a lot if you increase K. You need to increase K a lot. You could use a stronger model. Of course, in ARC itself, you're limited, so you would only be able to use maybe an 8B. I think this year the compute has gone up. So if you quantize, you might be able to use a Gemma 27B model. So it's probably not going to be stronger than the Flash model that I just tested here. You can improve performance then by one-shotting a lot. And I'll also just share, there's one more technique you can use to improve the voting, which we'll see come up in the test time training. If you have multiple programs and you're trying to decide which one to use, you can rerun on rotated or mirrored versions of these grids. So you can just take an example, or rather a task, and you can rotate by 90, then create another synthetic task rotated by 180 and one by 270. And you can run your program on all of those, and you can see whether the output generated, well, you can basically weight across the outputs generated. Now, this works well, basically making synthetic copies of the equivalent task, because the tasks are theoretically equivalent if you just do a pure rotation or a flip. So you should be just getting a flipped or rotated version of the solution. They should be invariant through those transformations. So by doing this, and then weighting across the outputs from those synthetic but invariant versions of the task, you can then potentially make your evaluation a bit more robust for the voting. Now, that works quite effectively when you're using a neural net, because the neural nets themselves are not invariant. And so by testing across these different variants, you're essentially adding more information to the problem. For a Pythonic approach or a programmatic approach, that's probably not going to bring as much benefit, because a lot of the Python programs themselves are going to have that kind of invariance already built in. So you'll just get the same answer in every case when you do the rotations or the mirrors. So that's a more of an advanced comment. You'll see that come into play once we get on to the next section. Okay, now for the last and probably most fun of the approaches, we'll take a look at test time training. So we're going to head into the README, which this time is very short, because the way I have developed it is by using an IPYNB, so a Python notebook, a Jupyter notebook, and we're going to run that on a GPU. So I'm going to start up using this link here. I'm going to take a powerful GPU just so things move fast, and I'm going to call it ARC TTT, and I'll start this up. Now, once I'm started, I'm going to upload this Jupyter notebook here, Trelis-TTT. And yeah, it's quite a long and fun notebook. It's going to take us through how to train a neural net based on some synthetic data for ARC. Then we're going to be doing test time training. So we will train on the training examples from the actual evaluation set. And then further, we will look at doing depth first search and see what kind of improvement that brings. You'll remember me describing that a little bit earlier. Okay, so we'll go to my pods here and connect, and then we'll open up Jupyter Lab. Now, a few notes on the inspiration here. One of the papers that is very good, if I look at MIT test time training, yes, this paper here provides a very good overview of how to implement test time training. So I recommend this one, and I've based a lot of this Jupyter notebook on it. Also, I recommend checking out MLST on YouTube. If you go to YouTube and then Machine Learning Street Talk, let's take a look here. There are a few videos that are particularly useful. One is this video here with Mohammed Osman, who's of Tufa Labs or Minds AI, one of the leading participants in ARC. And there's also a video of the winners from last year. Let's see if I can find it. Yes, this one here, Jan and Daniel making an appearance on Machine Learning Street Talk and describing how their approach works. So this is very useful if you're looking at particularly the depth first search approach, and also some of the algorithms around picking the best grid to submit, because you often generate multiple grids and you want to pick, well, the final two that should be submitted in the competition. So I'm going to upload this notebook I showed you, which is called Trelis TTT. And here we go. And I'll start off with the installation. In fact, I've started up a notebook here, but I've already run all the cells. So I think it may be most useful if I just walk downwards through the notebook without rerunning things, so we don't have the delay. Most of this runs extremely fast because I'm using a fairly small model. I'm using a Llama 3.2 1B model. Would you get better performance if you use a stronger model? You may get a little bit better performance. You can check out the MIT paper. They see some improvement going from 3 to 8B, and you could fit an 8B model, although it will be slower within the compute requirements. And you could even maybe fit that quantization aware training version of the 27B model from Gemma, or maybe even one of the Quen models. I'm not entirely sure if you'll get better performance. Interestingly, MIT found that the 1B and the 3B models were fairly similar, but perhaps as you move to ARC 2, you do need a larger model. Either way, you will run the installation here. Let me increase my screen size and install the requirements. You know, I think for those of you watching, it's possibly better if I look on a dark screen so your eyes aren't burned. Next, I've just set up a function here to clear old model references. Often I'm loading a new model, unloading an old model, so it's helpful to have a function that can just clear out CUDA. Next, we're going to load the data set. So we've got a simple script that's going to load up the data that's uploaded in beside our notebook. Now, I will show you this here. Basically, you should go and into the minimal ARC folder, which is publicly available now. And if you go to ARC data, you want to upload whatever split you're going to run. And you also want to upload whichever scripts you're planning to use. So we're going to use the training as a form of data to pre-train the models. We'll use the training challenges, and then we need the evaluation data in order to run our evaluation of our metrics or of our approach here. So don't forget to upload those scripts there, and they will then be loaded using this notebook. And this is going to run the typical data splitting task, which I talked about earlier. It's just going to split tasks that have multiple tests into two, so that every task has got multiple training examples, but then one test example. Okay, so with the code defined, we will now load, and we're going to load two data sets. We'll load a training data set, ARC train, and then ARC eval, which will be the evaluation data set. And for the evaluation data set, we can specify a subset. You can also specify a subset of the train examples, but we're going to load all of them. So we'll have about 400 training examples. But for evaluation, we're only going to evaluate on 20 problems, which will be the MIT easy problems. Now you can print out and look at the first row of ARC train. So for example, the first row is going to be this task here. And here's the training input, the output, and it should just have one test input output, which we can see just there because that's how the data has been split. Okay, so next, just for visualization, we're going to define a palette. So we've got a palette of colors for the 10 different colors, 0 to 9, and then a simple function for plotting the grid so we can see what some of these look like. And now we can test out this grid visualization. We can just plot out an arbitrary challenge 0 from the training split. And here you can see an input and an output. I'm just showing one input and one output so you can see how my visualization function is working. Okay, next we're going to create some pre-training data. So typically if you're going to compete, you are not going to just train on the training examples provided. You're going to try and augment them. And you're going to augment them to a much larger extent than what I'm showing you. But I am going to show you augmentation. So I'm going to start with the roughly 400 training problems provided by the challenge. So I'm going to start with these ARC AGI training challenges. And I am going to augment them in a few ways by shuffling the order of the training examples. So you typically have multiple training examples, then a test example. I'm going to shuffle the order of those. In fact, sometimes I'm going to have the test example back as the training and the training as the test. Second of all, we'll do some rotations, all the rotations, or some of them. And we'll also do some color shuffling. So you can just vary which of the 0 to 10 colors as long as you keep the relative colors consistent. And we're going to do these variations for expanding the training set. But we're also going to do these variations for expanding the training examples of the evaluation set. So we'll pre-train on lots of expanded training data. But when it comes to the test time training, which is in the exam, we're looking at the evaluation problems. We're going to take the training examples there, and then we're going to shuffle those. We're going to do color rotation. We're going to do rotations so that we have an expanded set that we can fine tune on. Now, I'll state this once and you'll see it more in practice, but the overall flow here is to pre-train the model on lots of expanded ARC data. And then right before running inference, so right before predicting an output grid for a given problem, we will train the model only on the data we have from the expanded training examples for that specific problem. So we have this really short fine tuning that will happen just before we do the inference for a given problem. And then we will throw away that model. We'll throw away the LoRa adapter, but we'll throw away that model and we'll go back to the model that's been fine tuned on the pre-training data. And then we'll again fine tune on a tiny amount of data for the next task. So there's actually training on a task specific basis. And that allows you to further specialize the model and improve the performance. Now, in terms of prompt setup, you might think, oh, we'll provide a big instruction here. But actually, because we're doing such heavy training and the model is just going to be used to the pattern, you can keep your instruction very minimal and have no pre-prompt. In fact, you could even simplify the tokenizer down to only contain, as I said earlier, just the numbers and maybe a new line. That is the most minimal approach. That's the approach that was taken by the winning solution last year by Jan and Daniel. It reduces the memory you need. It reduces the calculations, the number of logits you need to manage. So that's probably a smart thing to do. Of course, your model no longer really looks at all like a language model. You're really just using the backbone of the model itself. And it's debatable whether even some of the information in the actual Llama pre-training is useful for doing the inference. Okay, so something else I should clarify is there's the pre-training or the fine-tuning phase. And then there's going to be the task-specific fine-tuning phase. And it's useful to think of this in two separate buckets, because for the pre-training phase, our training data is going to be the training examples here, augmented, and the evaluation for that specific set. And it is useful to have an evaluation set because we're going to look at the eval loss and the training loss. So it is useful to have an eval loss. And the right eval set to have there is just a clean set of the 20 evaluation examples. So we want a clean set that's not augmented for the purpose of evaluation there. And then the second category we have is for the task-specific training. And here we have to look at it on a task-by-task basis. And for each task, the training set is going to be all of the expanded examples related to that specific evaluation task, but without the test example. And then the evaluation task is going to be the evaluation task itself, but there'll only be one row for the purpose of the eval set. So I'll repeat that again when I see it below. For now, we're going to focus on the pre-training. So for the pre-training, we need to define an evaluation set, which has got no augmentation. It's literally the 20 evaluation examples. So we're going to prepare the evaluation data set. There is an option here to drop the first training example if you want to shorten the context. I don't recommend doing that, but this just prepares the 20 rows of data. And the format is quite simple. You'll see it when we run through an example. It's going to concatenate the input and output training examples, and then it will concatenate on the test input and then the test output, which are the labels that we're looking for when we're evaluating. Next, we have our function for preparing the fine-tuning data set, which is more elaborate because it includes data expansion. It's got a few options here to add in shuffled examples, rotated examples, mirrors, color swaps. And we can also specify how many color swaps we want. We can also specify how many shuffles we want. Now, the shuffles are limited by the possible permutations, but I allow us to cap basically the number of shuffles to be included. There is one more parameter here in preparing a fine-tuning data set, and that's whether or not we include the test examples. If we're going to use the training data, then we will include the test examples. But in the case of doing test time training, we cannot include the test examples because we don't have the test outputs. So we will do omit test, and that means we will just be shuffling the training examples. So this is all pretty simple code. It will just shuffle, add rotations, mirrors, color swaps, and then allow us to hold out whether to include or not the test example. So let me just show you how to apply that by creating a fine-tuning data set. So this is for my pre-training. I'm going to set omit test to false because I can include the test examples if I'm using the training examples here. I'm going to add one shuffled extra. If you wanted better results, you should add more. I'm going to add all the rotations. There are 3 rotations. I'll add the mirrors. So there are 2 mirrors that can be added, so that triples your data set size, and add color swaps as well. And I'm just going to add 1 color swap. This basically caps the number of color swaps, but you could increase that to expand your data set too and probably get better results. So now you can see this fine-tuning data set, which was 416, I think, rows. It's now risen to just under 1,000 with this augmentation. You can see if I maxed out the augmentations, I would have even more runs, but I have not, just to keep the runtime fairly short. By the way, the training on this is just a few minutes with this H100, which is more powerful than you're allowed in Kaggle, but not that much more powerful. And you can see here, if I print out a random row, you've got this version of the 11852 CAB task that's got a swap, a shuffle, and it's got a vertical flip in it. And here is the task described. Now, I optionally allow for downsampling this further. If you don't want to run the full 10,000, you can downsample to say just 1,000, which allowed me to run the script faster. You would not want to do this if you want the best results. You would want to use all of the data and use it very augmented. So now we have our data sets. We have a fine-tuning data set, which has got 1,000 examples because it's downsampled. And we should also have an evaluation data set, which we do here. We build the eval data set, and it's just got 20 clean examples on which we want to evaluate. And we'll track the loss there to make sure that we're not overfitting. So next, we're going to train the model. We're going to fine-tune using unsloth. Unsloth works very well currently for single GPUs. So we'll install unsloth, and we're going to set a max sequence length. I know this is 20K because I measure later on how long the longest input is. For evaluation, it only needs to be 8K, but it needs to be about 20K for the full MIT training split. Of course, augmentations don't change the length, so That's fine. And we're not going to use quantization. We're going to train it in full 16-bit accuracy, brain float 16. So we load the model and tokenizer, and we're going to define a custom chat template, which is a simplified version of the default chat template. Now, at this point, I should say that I'm just going to use the base model. You could use the instruct model, but because we're pretty heavily moving the format of the answers away from the model's typical format, you could just use the base. I don't think there's much advantage to using the instruct model. And because we're not providing instructions, we're just training it on a very specific task. There's not going to be a whole lot of benefit, I think, to using the instruct version. So here I've got some print statements. I want to show you how the tokenizer chat template works. So I'll apply it to this first row of the eval set. So here's the raw first row of the eval set. And it's actually already been formatted here. And I want to show you that printed in a bit nicer form. Basically, we've got input, output, and then test input. And then we would have the output here, which serves as labels. Now, the middle is unfortunately being truncated, so we can't see it. There you go. Test input, test output, and then end of text. Now, if you're going to go further and improve performance, you probably don't even want to put in these words input and output. You probably don't want to put in these brackets. You probably don't want to put in these spaces. You want to redefine a tokenizer that is just going to keep each of the 10 numbers and possibly a new line. Possibly even some separator just to indicate that you're going to have the output here, because that will allow you, if you have some indicator, we're going to use this here as an indicator so that we only train the loss. We only consider the loss based on the tokens of the output. If you look at the MIT paper, I think it may be more optimal to train the loss on all of the outputs, including the training inputs here, which is not something I currently do. So I'm just training on the final test output, and maybe you would get a bit better performance if you trained on all of the outputs at once when you come to the loss mask. That's a fairly advanced comment. I'll comment on it a bit lower when we see it in the script. Okay, so here I've got a function to get the longest row in tokens. That's because I want to set a max length when I set up the model and the trainer. And you can see the max row is 18,000. So that's why I've set it to 20,000. Now here's llama for causal. It's indeed a transformer model, the 1B model. And we're now going to train it using parameter efficient fine tuning. So we're not going to train all of the parameters. You could do full fine tuning, but you probably don't have enough memory in order to do that on the allowed compute. You possibly, you would have enough memory if you do it on a 1B model. So that is a possibility. You could also use a method like Galore, a low rank gradient approximation method. So you could try that. You can also try increasing the rank. The rank is the size of the adapter matrices that you're going to train. And we'll actually freeze the main matrices and just train these small adapters. So I'm going to use a rank of 32. You could ablate using higher values to see if that improves. I'm going to train the attention and the linear layers in the MLPs. You could also train here, and I do, the LM head and the embed tokens. So this is training the embeddings. And I thought this would be useful because we are changing, are we changing the use of tokens? We're not actually redefining any tokens, so we may not need to do this. Are we changing the purpose for which a token's used? I don't think we are. So probably this isn't necessary, and it will add VRAM. But on the other hand, if you're going to redefine your tokenizer, then you probably do need to train the embeddings here. Okay, LoRa alpha, I always recommend setting this as the square root of the hidden dimension within the layers. So within your linear layers, you can check out one of my videos on LoRa fine tuning if you want to learn more about that. But for a 1B model, it should end up roughly 16 to 32. And we're going to use gradient checkpointing. And I always like to use rescaled LoRa. This automatically adjusts the training rate of the LoRa adapters, not the embeddings. They will be trained at the learning rate we set. But this automatically scales the learning rate of the adapters based on the size of the adapters. Broadly speaking, if your adapters are larger, you should be training more slowly because you're in a higher dimensional space. So you have to move more slowly. Whereas if you have a lower rank, then you're able to move faster because you're optimizing in a lower dimensional space. So here we have our fine tuning set, 1000 rows, eval set 20 rows, and we need a formatting function. This is actually a trivial formatting function, and it's required because unsloth requires a formatting function. If I was using directly the Hugging Face trainer and I had things formatted as either text or as messages, it would accept either of those and automatically find that column. Unsloth will only do that if you have a column that's named text. It does not allow you to have a column named messages anymore, I believe. And so you need this formatting function, which is a trivial function that just applies the chat template. It does not tokenize, it just applies the chat template and creates a column that's going to be passed in. So here you can see the tokenized, or not tokenized, but formatted column. You've got a user message, which is as follows. It's got the input output examples and should finish with the test input. And then it finishes by saying test output. And then you have the assistant message, which is literally just the test output here. They're the labels that we're going to train on. So again, we can see an example. And now we're ready to move to set up the trainer. So I'm not going to use gradient accumulation. It can cause some small errors with when you add up gradients across the mini batches. I'm going to use a batch size of 16. I think 32 would work as well here. And I'm going to train for 2 epochs. I'm actually going to train at a constant learning rate for the first one. And then I'm going to anneal with a cosine decay for the second one. This allows you to move quickly with optimization in the first epoch and then just gradually and nicely, smoothly decay down, hopefully to a local optimum. For learning rate, we're using a fairly high learning rate, 1e-4, because it's a small model. We're using some weight decay. This will be applied to the embedding layers, and then a modified version of this using rescaled LoRa, which will scale the learning rate for the adapters according to the square root, or 1 over the square root of the rank. So here I calculate the number of training steps. This is necessary to set up my learning rate scheduler, which basically will go flat, and then it will cosine decay. That's my cosine decay here. All right, so here we're setting up the configuration for training, and our per device eval batch size, I've set it to 1. That's fine. It's probably inefficient. I probably should set that to the same as the training size, because our eval batch is going to be 20 examples. So I could set it to 20 would be fine, as long as it's not going to overblow the memory. The reason I've set it to 1 is probably because down below, when we do task by task based training, we are going to have only 1 eval example because it will just be that task. So anyway, it's not going to cause an issue. I'm going to log, I'm going to do eval. I'll use Atom W for optimization. And what else? I'll pass all of that. So I'll pass the SFT config in here to the SFT trainer, pass the model, the tokenizer, and the data sets, the formatting function. Now, typically you would specify your optimizers here, but unsloth, because it overwrites the SFT trainer, it won't work if you just pass it in here currently. You have to basically update the optimizer and scheduler after you've set up the trainer, and you need to make sure that the internal builders don't overwrite again. So this is me giving myself hassle because I wanted to do a custom learning rate scheduler. If you just want to use a constant or a cosine learning rate, then you can do that directly with unsloth. The reason I like custom is because doing cosine, it just ends up, you don't make a lot of progress. Pretty quickly your learning rate falls. Whereas if you do constant, well, then you're not nicely annealing down to a low learning rate. So doing the constant plus cosine kind of gives you the benefit of both worlds there. Maybe I'm being a bit too theoretical, but I like the shape. So here we're going to decide that we'll only train on the outputs from actually the test outputs. And this is provided by unsloth, train and responses only. And this does allow you to train. It does allow you to train on the outputs. Well, it's designed to allow you to train only on assistant responses. But you could make use of this in a way that it will train on all of the outputs, including the train outputs. Here, let me say what it's doing. It's going to ensure that we only train on what comes after this string here. So anything between beginning of text and between this, which is going to be the training examples and the test input, is going to be masked, and it's not going to be considered from a loss standpoint. So in fact, you can see that applied here. If we apply it to one example, here's if we decode the full tokenized sequence, you can see it goes from beginning of text to end of text. But if we decode what is not masked, so what we're going to have the loss on, it's only going to be that test output here, which is what we want. Now, I could have rewritten this so that it would focus on any of the outputs. The way to do that would be instead, well, let me see if I make this a scrollable element. Instead of calling this test input here and test output, I would just call these input and output as well. So it would be uniform with the training examples. And then I would basically get it to mask everything between input and output. And if I did that, it would mask this, it would mask this. And if I had not named this as I have, it would mask this as well. So that would be an alternative way to mask the inputs and just train on all of the outputs here. But currently, as I said, I'm actually training only on the test output, which to me kind of makes theoretical sense. But in ablations on the MIT paper, they find that it's a little bit better to train on all of the outputs, which is a more probably information dense way of training. Okay, so we've set this up to only train on the final test output. We will run some GPU stats. So here we go. We've got 80 GBs and the model is loaded at this point. It's 1B. So at 16 bits, it's about 2 gigabytes, but then there's some extra as well. Actually, the 1B model is a bit more than 1 billion parameters. Plus we've loaded LoRa adapters too. So then we're going to, we can just print out here if you want for debugging to get the versions of the libraries you're running and then run the trainer. So here the trainer is running and it's running nicely because you can see the training loss is falling quickly and then slowly. And what's nice is our validation loss is falling also, and it's doing so pretty smoothly, which indicates that we are actually improving performance. And actually the training loss is still falling. Well, it's not falling at that last point, but the validation loss is definitely falling. And what I'm going to show you now is that you could train for much more and get much more improvement. I'm running for 1000 rows. That's 16 times 120. I already downsampled to 1000 from 10,000, and I didn't even expand my data fully. So if I'd have fully expanded my data, I probably could have gotten over 100,000 rows, and I could train probably to a much lower validation loss. And this is just using the training examples that are provided. There are also libraries or approaches like REARC, REARC, that allow you to greatly increase the size of your training data. And that probably would, well, it would allow you to generate a lot more augmented data too. And you could have probably millions of tokens to train on. Let me just show you the loss curves though for this. You can check out the final memory usage, save the model here. You can optionally push the model up to hub if you want, model.push to hub. This, by the way, will only push the LoRa adapters, which is good because it's more lightweight, so it's faster for reloading. And yeah, there's one other unslot specific comment here, which is that if you try and push the template I defined, it will actually cause issues when reloading with unslot because it's not a typical style of template, and unslot will think that there's an error with what you're trying to do. So that's why before pushing, I typically will set the chat template to none. So I'll get rid of the chat template, push it to hub, and then every time I load the model, I'll have to reapply my custom chat template, which is a little bit annoying, but that's currently the hack that I use right now. I think if you've pushed with just transformers, it probably won't give you that issue. Now, I said I want to show you some of the learning curves. So let's do UV run. I want to run TensorBoard, and I want to run it. I've got the logs copied here actually. So when I ran, I think it was yesterday, I think I uploaded my logs, and they're going to be in TTT. Yeah, logs. So my log dir is going to be logs. Let's see if this works. Yeah, so I need to do UV run with TensorBoard log dir. And it looks like it has started. All right, so this was my run, and you can see my eval loss is going down. So this is great. The other thing I like to look at is my grad norm, which is fine. You know, it's down at 1. It's actually falling from the start of the run. And the training loss is also going down. Sorry, I had smoothing on. So yeah, training loss, you know, there's a few bumps, maybe a bit less bumpy if I ran a batch size of 32. Here's my learning rate. You can see that flat and then cosine decay. And yeah, eval loss still falling. Now, earlier, I ran a different run, although it crashed. I can't remember why, but I ran it on a lot more rows. And yeah, you can see like basically the eval loss would keep going. It would go down to this point here. And presumably, if I kept running even more, there's some room for the loss to go down even further. So in this run of 1000 rows, I got to an eval loss of 0.1448, but it looks like I can get to at least 0.1244, probably lower, especially if I expanded my data even more. So that just shows you the potential. And now what we have is this fine-tuned model that's familiar with ARC. It's familiar with the training examples. And with that, it will improve significantly the performance. If you just run the raw model, especially with this chat template that we've made up, the model will definitely score 0 because it is not trained at all for that correct format. You can try and run an instruct model where you have a longer prompt and you instruct it to do something, but it will probably also score very close to 0 unless it's a bigger and much more powerful model that might score on a few of the problems. So with this model pre-trained, we can now run evaluation without doing any test time training and see how that performs. So we are going to start. We won't load the model here. Well, we won't load it because we're not running the notebook, but the model has already been loaded, so there would be no need to reload it here. And next we would run evaluation, just check the data set. We've got those 20 rows. And the way we run evaluation is by forward passing the model, getting an output grid, and verifying the output grid versus the ground truth. Now, when we run this, I think I just run with temperature of 0. So I take a greedy approach to the most likely next token at each step. And this will give me an output grid. As I described much earlier in the video, you can do better than that by using, say, beam search or using depth first search. So I'll talk about that in a moment. But for now, I'm just, I think, using greedy search. And I'm going to verify the output grid versus the ground truth. Now, again, this is a bit stricter than actual ARC because actual ARC, I'm allowed to submit 2 examples, whereas here I'm just doing pass at 1. So having defined a function to verify, I now define a solving function here, which is just going to set up the evaluation problem messages. So it's taking in the messages here. And then it's going to run inference using Onslaught's fast language model. I'm setting a max new tokens. I know that for MIT Easy, I don't need to generate more than 1,500 tokens. There's no thinking step here. It's just directly outputting the output grid. And you can see, yeah, it's pretty much a greedy approach because I've got temperature equals 0.01. So I've batched this into a script so that I can run multiple examples at once. I'm going to run the full, I should say multiple tasks. I'm going to run the full 20 tasks and see what kind of tally we get. So here we go. We'll start to look, and I'm just going to show the outputs so you won't see the inputs this time. Generated output, correct output. So it's got the first one right. The next one here, it's one where the output shape changes and it does not change correctly. The next one here, it gets correct. The output is just white. This one here gets wrong. This one here gets wrong. This one here, it almost gets right, but actually this is not right because the generated is using smaller pixel sizes and it's kind of downshifted it. This one here is wrong. This one here is wrong. This one here is correct. So we have 3 out of 9. It's like, yeah, this is not right at all. Not right. This one here is also wrong. Wrong as well. Yeah, it's just, well, it's quite a bit off on both of those. This one here is quite a bit off. This one here is, you know, somewhat right. The middle part is not correctly structured. This one here is completely wrong. And this one here is wrong. This one here is not even properly formed. You can see the top rows have got more numbers than these later rows here. So there are no ARC challenges with inconsistent outputs like that. This one here is wrong just because the left-hand side is not matching. this one here is wrong as well. So it got 3 out of 20 just by pre-training on 1,000 rows of training data with the Llama 1B model. So the question now is, how can we improve on that? And we're going to improve in 2 ways. First, we're going to improve by using depth-first search, and then we're going to improve by doing test time training. So unlike here, where we just took a greedy approach of the most likely next token, with depth-first search, we're going to decode in a greedy way right to the end, and then we're going to keep backtracking by 1 and look at the next most likely token. And we're going to multiply all the probabilities of the tokens generated to get a sequence probability. And we're going to keep the sequences that are above a threshold, I think of 5%. So we're going to do a pretty exhaustive search and keep all the sequences above 5%. And then we will nominate the highest probability sequence as our answer. Now in the real ARC, we would submit 2 answers. So we would pick the top 2, and that would improve our scoring. But here, I think we're just going to pick our top 1. Actually, I think I modified the script. We can see it a little bit down here, but I think actually I'm now accepting the top 2. So we'll see that a little bit down here. Either way, for the depth-first search, we will load up the model, and then we will move to setting up this depth-first search. Now, we're going to have this concept of candidates, and the candidates are going to be all of the output grids. And we're going to only keep the ones that are above a certain threshold. The threshold is here. It's 5%. Also, when we do decode, we're not actually going to do fully exhaustive search. So we're not going to look at all of the possible next tokens and their probabilities. We're just going to look at the top 5. Now, probably if I add a reduced tokenizer that only had the numbers, that would be 10 tokens and maybe a new line sequence. Then maybe you might as well look at all of them. That would be top 11. It does increase your search space quite a bit. But either way, you can reduce your search space a bit by only looking at the top K from each forward sampling step. And for batch size here, this just allows us to speed things up so that every time we do decoding, we're actually going to decode up to 64 in parallel. So we have this loop here, and then we have a little transformation so that we can always return a plain nested list. And yeah, I'm right. I do now have the ability to pick the top 2 solutions. So basically we look for the top 2 attempts, and we do so just by picking the 2 with the highest probabilities. And by the way, if there are no solutions returned above the threshold of 0.5, then we just return 2 blank grids. And I think if we've only 1, then we just return 2 copies of the same grid. So yeah, here's where we find the first distinct grid, second distinct grid, and yeah, then we return the generated output, and we return the 2 attempts here. Okay, so we're ready now to move to evaluation, and we're just going to iterate through evaluating each of these tests, and hopefully we'll do a little bit better because we're using depth-first search. So I'll do this fairly fast. You can see now there are going to be 2 solutions displayed. The 2 solutions are the same in this case here. It's actually found 5 candidates. Are the 2 exactly the same? Yeah. There's also something else here to mention, which is that because I have not limited the tokenizer, it is possible it's possible in any case, but it's even more possible because I have a broad tokenizer that you can have the same output grids, but you can have maybe an extra space in one case. And potentially that could be recognized as 2 different outputs, even though they're actually the same grid output. Okay, so that first question was correct. The next one was incorrect in both cases. So there was actually only 1 candidate, so both cases it's just a replica. The next one here, there were 3 candidates generated, and yeah, one of these was correct. So you can see in one case, it got the correct answer, which I believe is this one. And then the second candidate was this one. But because we're allowed to submit 2, one of them was correct. So we get this answer correct. Then 5 candidates for this problem. We're showing the top 2 here. This one here, we actually did get this correct now that we didn't get previously. So that's improving performance. Here, neither of them is correct. Here, one is correct. And then the second generated solution is incorrect. Here, This one is incorrect. This one here is also incorrect. And I'll move down quickly. Here we've a few where there are no candidates that are found for problems 13 through 15. This is just incorrect. And then we've no candidates for any of the last ones here. But all in all, we get to 4 out of 20. So we improve the performance a tiny bit. I'm not saying that's statistically significant. You would want to run a bit more than this, but you can kind of see the gist of why this might allow you to do better. By the way, it's also the case that because I'm now allowing for 2 answer submissions, that also improves the probability. Granted, when I do greedy decoding, there's only one possible answer in each case. So you would have no way, even if you're allowed 2 attempts, you don't have a way to generate 2 unless you move to sampling a second answer. All right, so this shows you depth first search. And now we move finally to the test time training, where we take this model that's been pre-trained and we subject it to further per task training. So for this, we need a data set that's going to be comprised of the eval data set itself, but omitting the test examples. We're going to do the augmentations though, because if we don't augment, we would just be fine-tuning per task on one single row of data, which is not a lot of data. Probably still would help, but we're going to augment it by adding shuffles, rotations, mirrors, and color swaps. Now, again, you could ablate increasing the amount of augmentation here, testing as well which augmentations help and which don't. But I'm just going to run with kind of a low level of each of the augmentations. So starting off with an eval data set of only 20, this has been augmented up to 480. And we're going to use this data set filtered on a per task basis. So we're going to filter for all of the tasks that have, say, this task number, which should give us, I think, roughly 40 training examples for every task when it comes to the task-specific training. So we'll filter our fine-tuning data set here. This is just a helper function that allows us to filter for a given file name or a given task name here. It's called file name. We have our formatting function, which is the same as above. And now we're going to iterate through each of the tasks, but our iteration loop for solving is going to be more complicated. We're going to load the challenge file name. So this is the task number. We're going to then filter the data set. And then we're going to define the evaluation set for the training. And the evaluation set is just going to be the specific row and not with augmentations. It's just going to be that specific row of the actual problem. So we're going to use that as the eval data set here. So if you want it to be perfectly rigorous, this eval data set should also have the test example filtered out, which I think in my case it doesn't right now, but it's not being provided as an input to the training or to the answer generation. So it shouldn't really have any effect. It's just for monitoring, just for observation. Okay, so then we'll clear any models in memory. We will load up the pre-trained model. So this is model to test time fine-tune. This is not the raw base model. It's the model that's been pre-trained on our expanded data. And then we're going to set the model up for faster inference. Actually, I'm not sure that line needs to be there because we're going to train the model first. We're going to define the chat template since I pushed it to hub using no chat template. Set up the optimizer, the training steps. Everything here is the same. We'll train constant and then cosine decay. And then we're going to set up the configuration. For the batch size, we're going to use a smaller batch size this time because our data set is quite a bit smaller. Let's see up here, I've set the batch size to 1. You could maybe set it to 2 or 3 or 4. That will maybe prevent a little bit of overfitting. So I haven't ablated that, and I'll just set the gradient accumulation to 1. So now we'll do the same things, define the trainer, optimizer, and learning rate schedule. Only train on completions, so same approach here. As discussed previously, we are only training on the final output, but yeah, I can kind of see increasingly for the task-specific training that training on all of the outputs, including the training examples, probably would be smart here. That probably would be smart. And then we can run our solver, which is going to be our 2-attempt depth first search solver, and get the result. So you can see within each iteration here, we're actually running task-specific training, and then we're going to run the solver and get the result. So this is all on a task-by-task basis. An extra comment here. The reason why it would be good probably to train on multiple outputs and not just the last one is because by definition in test time training,
you will always have a shorter context than the actual problem, because the actual problem is all of the training examples followed by the test input. Whereas when you're doing the test time training, you can only train on the training examples. So it's always one example shorter. And if you train on multiple outputs, it's helping the model probably to get accustomed to be able to respond to different numbers of examples. And that generalization, I'm guessing, this is speculation because I haven't ablated, but I can see the intuition why it would be better to not just train on the final output, but to train on all of the outputs. Okay, so we can run this, and what it's going to do is keep reloading the model. I think I literally reload the full model. There is probably an improvement here where you only reload the adapter, because technically we're only changing the adapter. There's an extra nuance though, which is that our adapters are not just LoRa adapters, they're also the embedding layers, because we're training both of those. So probably it would be good to ablate whether training the embeddings is useful or not, because if it's not, then your reloading is going to be even more lightweight because you're just reloading new adapters on top of ideally a merged model, by the way. So you would want to merge the adapter from your original trained model on the pre-training data, and then you just have to reapply the LoRa adapter for each of the tasks. Okay, so here are the results. We've one candidate. We get that first question correct. We retrain. By the way, look at the loss. The training loss is falling. The validation loss is falling. It's increasing slightly at the very last point, but broadly this behavior looks pretty good. It's getting the answer wrong though here. 4 candidates. But yeah, we've got a shape mismatch in all the cases. Third example here. We've got one candidate, that's why it's copied, and unfortunately it's wrong. Next example here, we've one candidate, and yeah, it's wrong. Next example here, we've 2 candidates, and one of them is correct, so now we've got 2 out of 5 correct. Next example here, 2 candidates, this one here is correct, so that's good. Next one here, actually it fails, I think, to generate any candidates on this problem here. Now you could also lower your probability threshold, see if you get any useful candidates. That's another ablation you might want to try. This one here, it's got 1 candidate, so they're copied and it's correct. This next one here, 3 candidates, and yeah, unfortunately none of them are correct. Next one here, 2 candidates, and one of them is correct, so we're up to 5 out of 11. So you can see we're already beating here at 11 questions, we're ahead compared on not having done task specific. 5 candidates here, but that one is difficult to grade just by looking at. I can see they're wrong though. Next one here, problem 14. Problem 13 had no candidates. Problem 14 had no candidates. Problem 15 has got 1 candidate and it is correct. So it's copied and it's correct. And next problem here, 4 candidates, and it looks like we've got 1 correct as well. Yeah, this one here is correct, and this one here you can see it's slightly incorrect. So actually the second highest probability there ended up being correct, 7 out of 16 now. Problem 18, this looks like it doesn't match, so that's going to be wrong. Problem 19, it looks correct here. So we've got 2 candidates. The first one is correct. So we're at 8 out of 19. And then for problem 20, we have 0 candidates. So yeah, by using this test time training, we've gotten from, well, either 3 or 4 up as far as 8 out of 20. So you can see by doing this task specific training, you're able to, yeah, very meaningfully boost the performance. Now, there's one other key trick that's used by the winners of last year's ARC competition, and that's when you are doing the final decision on which submissions to enter. Because you can see if there's only 2 candidates above the threshold, you just submit those 2. But if there are 4 candidates or 5, and if you say lower your threshold so you get more candidates, now you have to choose which ones to pick. And yeah, probably, you know, selecting the highest probability makes sense, but there's an interesting improvement that they introduce, which is instead of just solving it on the actual problem, solve it on rotated versions. I mentioned this earlier, or mirrored versions, or color swapped versions. And if you run separately on those invariant versions, and I say invariant because the answers should just be flipped, rotated, or color swapped
versions of the solutions too. You can then aggregate across those different invariants, and that should give you a more robust predictor of what the best solution is going to be. So essentially you rerun, but with invariant versions. That may not be correct language, but basically rotated, flipped versions of the input problems. And then you get the outputs, and then you can majority vote across those as well. So that avoids you having the noise of just looking at the actual problem as given. And it gives you a more kind of holistic description. Because as I mentioned, neural nets are not rotationally invariant in the answers they produce. They're not color invariant in the answers they produce, especially if they're not very well trained. And so, yeah, you can reduce some of the noise and further improve your performance by doing that increased sampling and then voting across those kind of invariant categories. Okay, so that brings us to the end of this test time training, and also to the end of looking at this repository. You can, of course, check it all out because it's online now. What I want to talk about very briefly is the Trelis ARC AGI 2 team. Trelis is gathering a team to compete in this competition hosted on Kaggle. And there is a short questionnaire here if you're interested in applying for the team. The prize itself, the terms are set by the ARC prize itself and are governed by Kaggle rules. By default, the prize money is split among team members unless there's unanimous agreement. So these are the prize terms here as set by Kaggle. And yeah, the process for picking the Trelis team will be a short interview. I'd recommend that if you apply, you've done at least some tinkering and created some repos that I would be able to read through and that we could discuss together on a call. The target is to get started with some team meetings to advance progress already in May, and then proceed towards a final team selection by the end of the quarter. Also open to sponsors, so you can submit an indication of interest if you are a company operating in this space and like to benefit from some recognition from videos published by Trelis on this topic. So that's the overview of ARC AGI. I think it's a very fun competition, and let me know as usual if you've any questions down below in the comments. Cheers, folks.